Hey there, everybody. Today is March 1st, and we are checking out the Drake equation, or the probability of alien life. So far in class, we've built planets. We've figured out if it's possible to transform them to create the conditions that are appropriate for human life. We've talked about what it takes to make life in the first place, determining, water and carbon are our best bet. And then we were talking about the CHZ lab with different stars. Where exactly can we find liquid water? That's dependent on the mass of the star, how that'll determine how long it lives and how much energy it puts out. But now we're to the point where we have a good enough idea of how life the things that life requires. So let's take a look at the probability of that actually evolving. This is based off of, clearly, this PowerPoint is based off of one by Brian Jackson at Boise State. He teaches astronomy over there, and he's a brilliant astrophysicist, specifically a planetary scientist evaluating Martian dust storms. So all of this comes pretty much straight from him. And there's just some minor edits that I made to this document that we're going to be going through. So this PowerPoint and video is meant to go hand in hand with the Drake equation worksheet. So you'll want to make sure that you got this bad boy sitting right here with you, all right? This is something that we're going to be working through to help us put us in the mindset of what it was like to be Frank Drake, how you determine and even go about answering a question as complicated for how much life is out there. Astrojack.com is Brian Jackson's website. I would very much encourage you guys to check that out. He's got all kinds of stuff pertaining to his modern research, his outreach programs, and events like Boise State's First Friday, excuse me. So, the Drake equation is a really elaborate thought experiment. We have seen life evolve only once. So how do you even go about developing a probability for how much life could have evolved if we've only ever seen it once? Well, it requires us to make a series of assumptions. So let's get in the mindset. Let's first just think about the scenario of how many female students at Timberline will pursue a physics degree while in college or at college. So you'll notice that this is the first portion of your worksheet here. I'd like for you guys, take a second, just pause and answer this. What do you think? What do you think is the number of female students at Timberline who will get a physics degree at college? We're going to go on and estimate some of these things, though, using this table here. That is displayed on my PowerPoint. You'll want to kind of keep that worksheet right there with you. But here's the series of assumptions we might want to make. We're going to have to think, well, how many people are there at Timberline altogether? It's important to recognize that we have to go through this thought process, because you guys know how it is when you put out surveys for your classmates, or even when the announcements come through, like how many people are actually able to process and hear and take that information somewhere else. Like, let's assume that we can't just send out a blind survey and ask people, because you know what? We can't ask if aliens exist, because there's no one to answer as far as we know. So we have to make this series of assumptions. First, we need to figure out what population we're working with. How many total people are in the building? Once we figured out how many total people are in the building, we can figure out, well, what fraction of them are female. So Timberline has class sizes, varying between like 300 to 400 at different times. So let's say that just in general that Timberline has let's say we have 1,200 students total. About what percent of those are female? Probably about 50%, right? So we'll have 1,200 here, maybe 50% here. It's important to note that a 50% written as a decimal, one that we can multiply by, will be 0.5. So you'll probably want to put 0.5 right here. Then we have to figure out, well, what fraction of these students, of these female students at Timberline, notice how we're getting more and more specific. This question right here, or this fraction right here, is dependent upon these other two. What fraction are going to go to college and continue? Well, we're probably looking. Timberline's got a pretty high value, but maybe just throw something in there that you're thinking. You're welcome to have a number that varies from mine, but maybe we're thinking like, I don't know, 60%, or maybe even 50%. Down below, how many different degree programs do most colleges offer? Guys, colleges have a lot of different offers. This can be in the hundreds sometimes. So let's say we got a relatively we're talking relatively small colleges. Let's just take a nice even 100, okay? We'll type that 100 in for the number of degrees. But then, not only that, we have to take in the idea of, or like consider, well, how long does it take to finish that degree? Because it's not a one for one trade. They don't just go to college and have the degree after 1 year. It takes them time. So um, we have to figure out how many people are going to ultimately achieve that, and it takes maybe 4 years to get that physics degree. So we've got values of like 1,200, 50% female, maybe 50% continuing education, maybe 60%, maybe 100 different degree programs at a given university, and 4 years. If we multiply all those values together, it'll give us a total number, the number of total students at Timberline, the females specifically, who might go about finishing a degree in a 4-year program. But we're not going to dwell too much on the correctness of this answer. What we really want to look at is how this all comes together. In recent history, we've been you've heard where this exoplanet discovery is becoming more and more common. This animation was back in 2017. Google Doodles did a little animation to celebrate the discovery of the TRAPPIST-1 system. The TRAPPIST-1 system is one that we're going to be talking about quite a lot throughout this presentation. But TRAPPIST-1, we found several exoplanets all within a habitable zone and just in a single batch of planets. So this is kind of where, in modern society, we're asking this question more and more, like, can we live other places, or is there already life there? The Drake equation itself kind of has a history with this telescope. This is the Green Bank telescope, and this is one that Frank Drake himself utilized to observe various star systems. So radio telescopes like this, as we'll talk about, is just one method. A good method by which we might be able to discover intelligent life. But even though we got these bad boys looking out at space, there's only so many of them, and there's so much out there. So, like, we can't feasibly send out a survey to all of the students at Timberline to figure out how many females are going to be getting a 4-year physics degree in college. We can't ask the aliens, so we have to calculate. There's a lot of information here, but this that you see is the Drake equation sitting right here in the center. We have n r star times f sub p, n sub e, f sub l, f sub I, f sub c, and a capital L. We're going to talk about each one of these in detail, okay? And you'll notice that it's listed on your lab, so you don't even necessarily need to write all this down. It's all there for you. So let's look at each of these one at a time, and let me just go ahead and shift on my page so we're in the correct place. As far as A3 and A5 go, guys, you'll want to maybe pause a little bit earlier or soon and get all these questions kind of figured out once we're in the mindset. But we are on to part B now. The Drake equation. We've got all our different labels for this right here. But let's look at each of the variables one at a time, and we're going to run through the same procedure. What value do we have for the number of stars? What value do we have for this and that? And we're going to ultimately end them all to multiply them all together, and you're going to come up with an estimate. How many civilizations do we think are out there? So, back to the PowerPoint. One at a time. N. This is what we're aiming for. Capital M, or capital N, the number of civilizations in our galaxy in which communication might be possible. How many other civilizations are out there within the Milky Way itself? R star. the average rate of star formation per year in our galaxy. So, how many stars are being developed? Obviously, this isn't a stagnant number. We know how stars form, we know how stars die, but with every single one that's added, we're increasing potential for life to exist, I guess. Um, F sub p. Notice just a quick point here. F with the little p next to it. That p doesn't represent anything except for a way to distinguish it from the other f's, the other fractions that are going to be in this equation. So we're not multiplying f by p. It's just like, hey, this is a little note I'm going to put off to the side, just like a little asterisk almost, saying this is what this specific f stands for. This is the fraction of stars with planets. Because, yeah, we can make stars, but how many of them will have planets? But just like at Timberline, we've talked about how many total students are there. Well, what percentage of them are female? We got to take it even further and say, well, what n sub e is the average number of planets that can potentially support life per star with planets? This clarification right here is very important. Per star with planets. Just like the female students at Timberline, every single one of these values is dependent on the previous being true. Okay, so you can't have planets around a star if it didn't form in the first place, just like you can't have an average number of planets if some of those stars don't have planets. So n is based on these assumptions, and it is the average number of planets that can potentially support life. Maybe the ones in the habitable zone is the way we would consider it. These last three are all dependent on the evolution of life. Now that we have our place to now that we have a planet, we need to follow a progression. Well, if it can potentially support life, what fraction will go on to support life? From there, we have to say, well, what portion of that life will be intelligent? And once we know that, maybe we've got a bunch of monkeys, but can they develop some sort of technology that we can actually read and see? Or can they build telescopes? Can they send radio signals? Can they reflect a giant mirror to give us a flash signal? So these last three are all that life portion, and these you'll find are a little bit more ambiguous because, again, how many times have we ever seen life evolve? So far, it's one. So let's look at each of these. Well, I guess lastly, we have to consider how long it takes to finish a degree, right? The length of time that such civilizations, will release detectable signs into space. We're looking at the odds of detecting them, right? So it's important to consider, like, did they just shoot a single flashlight into the sky and hope someone would see it before they turn it off in 2 seconds? That doesn't leave you a very big window to find it. So we have to multiply by the length of time here. So here's what we know. We're going to go through one variable at a time. And again, this is where we're going to be putting some values in on our chart. The number of stars that form each year in the Milky Way that are suitable to host a planet. You can type values in here, but please also feel welcome to take notes in these columns just to say, like, how did we come to this number? So, like I said, we're developing about 1 solar mass per year. 1 star forming in our galaxy per year. That doesn't seem like a lot, but the Milky Way's already got quite a few of them out there, but we're adding to the number that we can find. Because if that civilization already exists, this is going to allow us to continue that forward thought and say, well, here's how many more can exist moving into the future. Let's look at these two now. The fraction of stars with planets and the average number of planets that can potentially support life. Let's have a quick discussion on this stuff and start with what we already know. The Milky Way is pretty dang big, guys. There's a lot of stuff in there, and we need to take account of how many things are actually out there can be kind of tricky. So let's maybe just focus in on our solar system. Within our solar system, we have 8 planets. But as demonstrated here, not only do we have 8 planets, we have several objects orbiting those planets. We got our moons. Maybe we got like Io and Ganymede over here. We got Enceladus somewhere over here. But we got 8 planets in our system with various numbers of satellites, and we need to be thinking, well, big picture. How many how many stars are there per planet? Because even though we know what we have here, only one of these 8 is capable. But our first count is there's one star, 8 planets. Is that universally true? Does every star have 8 planets? Part of a problem kind of emerges here because remember we haven't been doing this for very long. The amount of planets that we've been discovering has been limited to the last 20-ish years. Of course, we're finding more and more and more and more. And you'll notice that we've got ups and downs. Sometimes we're looking in the right places. Sometimes we got the funding. Sometimes we have more interest. So years like 2014 and 2016 can happen. But what we're finding as we look out into space is there's a lot of planets out there. Using those methods like radial velocity and radial velocity, that was Doppler spectroscopy, or transit, or I guess any of these other methods listed here. We're finding a lot of planets, and what we're finding is there's about 1 planet per star on average. Yes, the sun has 8, but some don't have any. There's other situations where you have a binary star system, 2 stars, maybe that share a single planet. So on average, we got about 1 star per planet. So the TRAPPIST-1 system, the one that I've been alluding to, the one that was in our Google Doodle. What we found in the TRAPPIST-1 system is that we've got like this relatively small star, and we have 1, 2, 3, 4, 5, 6, 7 planets around this star. And a lot of them are considered super Earths or very Earth-like. What's crazy about this is all 7 of these planets are in the habitable zone. Oh my gosh. This is a crazy place. Like if we were thinking, you know how they're thinking about doing missions to Enceladus or to Titan or to Europa, and they're like, let's go look for life. Imagine if we could reach outside our own solar system and pick out what's our best hope, what's the best place to find, or best chance that we're going to have to find a new place to call home or to find life. TRAPPIST-1 is looking good. 7 Earth-like planets in the habitable zone. Insane. You'll notice though that because that star is so small, all of those planets fit in this tiny little orbit. If you were to compare that to the scale of our solar system, all within like not even half the orbital radius of Mercury. Crazy. So again, so far we figured out that our first value, the average rate of star formation, is 1. But we found, based on our lots of discoveries in the past 20 years, about 1 star per planet. F sub p is 1. About 1 star per planet. And we're finding that as a result, we're going to put in a value here for 100%. Not all stars have planets, but there's enough planets out there that you can look at them relatively equally. Okay, that's important to know. Not every star has a planet, but if there's about 1 planet for every star, that means about 100% of stars have planets in the big picture, if we're comparing that ratio of planets to stars. Where our interest comes in here is the average number of planets that can potentially support life. Well, if we're talking about TRAPPIST-1, we got a 7-to-1 chance here. Whoa, 1 star, 7 planets? That's insane. The problem is it's not always that optimal. We know, for example, in our solar system that, Earth and Mars, they currently sit within or near the habitable zone, and Venus is kind of on the fringe of that as well. So we might have 3 out of 8, maybe. So we got 7 per 1 star here, 3 out of 8 here. But then something we have to consider is there's like blue supergiants out there. You'll remember from the CHZ lab that really massive stars, they are not likely to support life. They put out too much energy, and even though they have a big CHZ, they burn out real fast. So we might not necessarily be able to consider those. So for every Earth-like or solar system-like or TRAPPIST-1-like system, we got a lot of stars that we just cannot even count. So what we're going to do is, if this value is 1, we got to recognize, not every planet can potentially support that life. We got like 3 out of 8 in our system. TRAPPIST-1, yeah, that's a super good chance. But let's say that there's about a 0.25 or 25% chance. 25% chance that they could support life. Maybe 25% of all planets are in the habitable zone. So that value for n sub e here, Earth-like planets essentially, we're going to say it's about a 25% chance, 0.25. This is where we get a little tricky. This is where our science is a little fuzzy, but the fraction that can go on to support life, let's focus in here. We know that the Earth early on was a giant hellscape. This was not a good place to be. We had bombardment. We had extremely high temperatures. Heck, we didn't even have an atmosphere for a while. The thing is, life finds a way, guys. Even though Earth was totally chaotic, even under some of these early conditions, life was starting to evolve. Ones like we were talking about in the last discussion, where there's, these microtubules in the Nouveau-Agatuque greenstone belt, or green belt. These stromatolites, like these things survived that bombardment. They were starting to evolve under that bombardment in these early stages. One of our next labs is going to be about extremophiles, these organisms that can survive under the most extreme circumstances, some of which can even survive the vacuum of space. This doesn't mean they like it there, but it means that they can survive it. They can at least endure until the conditions improve. So when we look at this number, remember, we're eliminating here. We went, or not eliminating, but specifying here. We started with the average rate of star formation. We get about 1 new star per year. The fraction of stars with planets is about a 1-to-1, where 1 star per planet. And then the average number of planets that can support life is about 25%. As we move here, remember, we need to assume that all the rest of this is true. We're already looking at planets that can potentially support life. So far, again, we've only ever seen 1 example of life emerging. So this number is very much up to some scrutiny. But a lot of scientists, they'll look at this. They'll look at the fraction that can go on to support life, and they'll pause and they'll say, what do we know about Earth life? We know that Earth's life, like the stromatolites, is very hardy, very durable, very persistent. So if you can get life, complex chains that are sustainable and replicating in even the craziest conditions, like the bottom of a volcanic vent or in the midst of some acid, if that can happen, we're going to assume that there's a 100% chance. Whoa, okay. Before you start punching your monitor saying that's a crazy assumption, like, again, remember what I said. If all of the rest of this is true, if we are already considering a planet that could support life in the CHZ, based on the life we know, it is very hardy. It is very persistent. It can withstand crazy environments. So if life can exist, it will. This is a very big assumption. And those of you that are feeling like punching your monitor saying that's ridiculous, you know what? I kind of agree. I don't think we can look at all planets with equal perspective, but a lot of scientists, including Brian Jackson, a planetary scientist at Boise State, they say this is somewhat of a reasonable assumption. This number we can assume is pretty high because we are already assuming that the planet could support life, has the potential to. So if life can evolve, it will, and that's where this 1 or this 100% comes from. Let's clump these two together. The fraction that can go on to support intelligent life and the fraction that will develop a technology detectable from space. If we look at the Earth's history, this is that geologic time scale just revamped here. We had the Hadean Eon where we have the bombardment and all that crazy stuff going on. And in this last 540 million years, the Phanerozoic Eon, that's where all life exists. back in the Cambrian explosion, we got these a whole bunch of diversified uh, ocean dwellers, and we start to evolve things like fish over here, bugs here, we get some lizards, and then we get the dinosaurs and mammals and flowering plants come out here. We sit right here at the end. We're talking about intelligent life capable of communication. It took us a long time to get here, right? It took us a very long time to get here. And not only that, our ancestors arrived like, let's get that out of there. Go away. Like the Australopithecus afarensis. I don't know how to say it, but we get early ancestors of humans back like 4 million years ago. And it wasn't until like, 2-ish million years ago that we start to get things that are somewhat recognizable to get us where we are today. It takes life a long time to come around, okay? But we have a lot of assumptions that we're making again. If we look at these, we have to assume that all of this is true, that based on this portion of planets that can possibly support life, if it can, it will. And if that life is capable, if we're in an environment where that life can continue, we will assume a 100% success. If life can exist, it will become intelligent. This is another huge leap in logic, but this is supported by scientists, at least in the sense that if it can go on to support life, that means that it's in the habitable zone of a stable star. So it's probably going to be around for a while. So we have the time. If you can develop life in the first place, it's naturally going to reproduce and evolve and do these things. So it will very likely become intelligent. And if it becomes intelligent, it's just as likely to develop technology. So again, big assumptions, but we're going to roll with it here. So far, we've got one star per galaxy forming every year. We have a 1-to-1 ratio of stars with planets, about a 25% success rate in terms of getting planets within a habitable zone. We're going to assume that if it's in the habitable zone, it's going to support life, and if it will support life, that life will become intelligent. But now, we have to think about how long it takes to finish the physics program. If we want to figure out how many people are currently in the physics program, we need to know how long they're going to spend in it. So how long are aliens going to be able to release detectable signs into space? This is a big one. We have to think about our history and what we have been capable of doing as the one sole organism that we're aware of that has been able to do this. We have to think back into history, and we'll see back at the Cambrian, 542 million years ago. This is the diversity of life in terms of like, I don't know the exact scaling, but let's say this is millions of species. Okay, you'll notice that this kind of goes up and down, but you'll notice there's situations like at the end of the Permian, huge drop down to like 4% or 4 million species out of what, like 53-ish million? Giant drop. This was the Earth's first major mass extinction, wiping out a huge proportion of life. Then that life kind of resurges, we get some drop-offs, and then here was another major one. The KT extinction that wiped out the dinosaurs. Big drop. But you'll notice through here there's lots of ups and downs. Like from here to here, maybe 200 to 150 million years ago. And then from 150 to like, what would this be, about 60? Scientists are thinking on average, there's about 60 million years per mass extinction. 60 million years per mass extinction. How long does it take until that next catastrophic event occurs? This is going to help us inform the value here. If we're thinking reasonably for humans right now, how long have we been able to release signs into space? We've been building radio telescopes, and we've had televisions for, I guess televisions aren't doing this, but like satellite dishes and stuff. We've been doing this for about 60 years. We've been pumping signals out into space, looking for things, sending messages. That's when the space programs were first starting up about 60 years ago. So right now that number is about 60, but this is open to a lot of interpretation. One thing that we might change here is the length of time such civilizations release detectable signs. While we've only had 60 years, how long do you think we'll have? How much longer will we continue? So while as a class, we're going to go to our lab and type in a number like, so far we have one. Ooh, hello. So far we have one. We have a fraction of stars with planets. That's a 1-to-1 ratio. A number of habitable planets, we got 0.25. If life can evolve, it will. So far, we've only been communicating for 60 years, but we know that this question isn't asking, well, no, how long have you been, but how long will you? How long will you spend in college? How long will you be able to pump this information into space? If that mass extinction trend stays stable and, we don't kill ourselves, we could be talking numbers like that. Oh boy. And that's assuming that natural causes are able to get us and we haven't found a way off of the Earth. This number could be greatly increased. So as we throw these numbers into a calculator, keep in mind that these have some flux, but especially this one. Okay. Like I said, 60 million years, that might be the amount of time that we have until the next asteroid gets us. But what if we moved on? What if other civilizations have already moved on? What you see here pictured is what's known as a Dyson sphere, a hypothetical theoretical device that can be built around a star so that all of its energy can be absorbed. You can essentially think of all of this as like solar panels surrounding that star to harvest its energy. And if we get to this point, that number at the end, the amount of time that we can survive, that skyrockets. It might not just be 60 million or 2,000 or maybe we start World War VIII in a few hundred years and that's the end of us. But if we can get to this point, oh boy, we're living pretty much indefinitely. But it all comes back to this. This is where we started. This one little thing here is where we very first started to search for extraterrestrial life. Frank Drake came up with the Drake equation, and that allowed us to come over to things like this and make a calculation. So what we need to come up with is an estimate here, all right? So I need to switch over around my screens a little bit, and we're going to go here, okay? The Drake equation. This will be used to calculate those values. And you can spend some time experimenting with this, right? Let's use our class values. One number of stars that form in our galaxy per year. About 25% of those are capable of supporting life. Liquid water, we're talking like, fraction of stars that have planets, I messed that up. 100% have planets, 1-to-1 ratio. 0.25. If life can develop, that gives us values here for 1. And let's say that we only have 60 years to develop, like the world's going to end tomorrow. Let's calculate and see how many communicating civilizations we would expect to be in the Milky Way right now. Oh my gosh. That's crazy. 15? Could there be 15 other civilizations out there? Of course, you'll recognize that this equation is up to some scrutiny. You might say, okay, life can develop intelligently, but I don't think they're going to get smart enough to be able to do that before they die. So, actually, yeah. But play around with these numbers. Write some observations in the note column as you play around with these numbers. Let's do it like right off to the side here. Type out an estimate that you think is more reasonable off to the side, one after you've made some adjustments. Record the values that you put in your notes and like off to the side, maybe put like a slash here and say, oh, well, I changed this to 4 or whatever. Of course, that number is not much subject to change. That one's been determined, but change some of these values and play with it a little bit and see what it's like. Because you'll notice that even as you change these, let's say they can communicate for 6,000 years, but fraction of planets where life develops. Oh no, now we're that. Let's reduce that. Um, Life will develop on maybe 75% of those planets. And yeah, sure, that life will become intelligent, but I don't think they're going to make it very far. Let's say only half of them make it. Oh, oh gosh. What we're going to find here is that even as we start changing some of these numbers, it's still likely. Oh my gosh. Whoa. Go ahead and pause for a minute and play around with this calculator a little bit. Type in some numbers you think are feasible and leave me some notes in your lab so I can see that you've played around a little bit. Unpause. Coming back. Let's check out the last page of our lab. Of course, by now you should have all of this filled out. Any notes or thoughts that you have about these different factors, please type them in over here to jog your thoughts. And then your estimate that we came with the class right here, but your more reasonable estimate, let's put that off to the side. Okay, so now we need to review some of these questions. And all of these are just kind of critical thinking based. I want you to answer as honestly and openly as you can. These questions don't require much in terms of accuracy. I'm not looking for something correct, but I'm looking for you to think here. For example, our solar system gives us insight. How would the value of n, which was the number of habitable planets, change if we start including things like Mars and Venus and then the Galilean moons? Like Europa could potentially have life. Like, what would happen to that value? What do you think? Down here with part C, you're going to need a calculator. Okay? You're going to need to type in values for these and run the calculations. For example, you're going to calculate D here, the distance between civilizations in light years. And that's going to require you to do some scientific notation and type in fractional exponents. One thing I want to point out is that n here, you might be thinking, well, what's n? I can't solve this equation without some numbers. Well, you calculated n. That was the final result. So use some values for n, either the one that we came up with as a class or the one that you came up with yourself. And you're going to plug that in here, here, and play along with that. So we're going to talk more about the Fermi paradox in general later, especially tomorrow. But if we're getting such big numbers from the Drake equation, where's the life? If life exists, then where is it? Why can't we find it? We'll talk more about this paradox in our SETI discussion, but at this point you have the knowledge that you need to finish the lab. So please continue forward, wrap that up, and submit when you are completed. Do your thing. We've basically done everything except for those final questions. So finish that up and submit. I'll see you guys tomorrow.